So good afternoon, everyone. My name is Rehan Bhatti. I think Anne has already introduced me, but for the short intro of myself, I have a PhD in material science. Since my PhD, I'm working at two different organizations. Currently, I'm a part of University of West England, Bristol, but before that, I have worked at Queen Mary University of London. I would like to thanks the organizers, and it is a pleasure to be here today and share my recent advancements in the field of material science. Let's proceed to the talk. Our research is focused on developing a novel chain-oriented polymeric material with an exceptional photo actuation performance while maintaining the polymer flexibility. I would like to start with the famous quote of Honorable Richard Feynman, who proposed that the mechanical deformations within the materials at their molecular level can be generated using stimuli, either internally or externally. For example, electricity, heat, temperature, and most importantly, light, which will be the base of our research. And here are some examples of the stimuli and their response. The most common ones are light. We can see these examples all around us. The others are heat and temperature, moistures, and humidity. Actuator materials are not new to the scientific community. This field is being studied from a very long time. Just to give a brief intro, what actuators are, an actuator is capable of harnessing energy from the external source to trigger changes within the material, the internal structure of the materials, and that leads to some kind of mechanical deformation, for example, twisting, bending, or sometimes in terms of actuation stress, strain, or some kind of work that can be generated through an actuator. And there are a wide range of actuator materials are out there, which has been studied extensively, ranging from organic materials to inorganic materials. The organic materials are subclassified into natural materials, for example, natural muscles, proteins, and piezoelectric biomaterials. The synthetic polymers, for example, hydrogel, liquid crystal, shape memory, thermoplastic, and high modulus polymers. And inorganic materials like shape memory alloys, piezoelectric materials, are magnetostructive materials. The most important thing about these actuating materials is that all of these studies are trying to harness the output in terms of mechanical deformation. Some of them, they want a physical movements to be shown or studied, and some of them are actually trying to harness the power of this actuating materials. For example, the actuation stress, or the energy, or the work that can be done with the actuating materials. A good actuating material or a good actuator would be the one that can give us a rapid response that does not degrade or generate a hysteresis in its response, and the response should be reversible. But the problem with the existing materials is that most of them are very slow in their response. It takes from minutes to months to get the response, and they involve some kind of hysteresis, a degradation, does not respond equally or consistently all over again. And some of them, they does not able to get back to their original positions once the work is done. So we need some external source or another medium to get them, make them usable all over again. And this became the base of our research. We anticipated that an actuation mechanism is therefore highly desirable that permits non-contact, ancillary-free, and controllable actuation mechanisms. And we aim to create actuation stress, in particular the specific actuation stress, by using the materials, the specific materials for that purpose. And we wanted to get the response as quick as possible. You can say that for rapid response, and reversibility is one of the top priority for our work. Now I would like to show an overview of the existing actuators. This graph was generated actually before the start of our research work. And this graph is actually showing the trend of the existing actuators out there in terms of specific actuation stress and actuation stress. As you can see over here, it consists of metals, ceramics, composites, and polymers. And metals and ceramics are actually aiming for high actuation stress, but the polymers, which are usually perceived as soft materials, are aiming to get more actuation stress. But if you see closely, there is a potential in this chart that has not been explored before. The polymers, all of the polymer actuators, they are aiming for actuation strain rather actuation stress. Usually polymers are perceived as soft materials, but this is not the case. We all know that polymers can be made stiff by chain orientation process. And we can study to see the feasibility of stiff polymer actuators. The good thing with the stiff polymer or the chain-oriented polymers like polyethylene is that they can retain their flexibility. They are in the polymers, they are recyclable. They can accommodate a wide range of photoresponsive additives. They can undergo photomechanical deformation and can easily be modulated. So we think that polymers are a good candidate for creating an actuator, but we should also consider the possibility of creating a stiff polymer actuator with a concentration towards achieving a high actuation stress. And that's why we started our work to see the potential in creating a stiff yet flexible polymer actuator that can be remotely addressable using commercially available raw materials and through industrially viable route. That was the aim of our work. Let's talk about the recipe. I have divided, in the next few slides, I'm going to show the three most important elements to create an actuator. In order to realize actuation in these materials, which I'm going to prefer as a host material from now onward, stimuli are usually indispensable. As mentioned before, if we wanted to get a fast or rapid manipulation of these actuating components or materials or the host materials, we need to see a source which can transmit energy from one part to another part. We also wanted to achieve a remotely addressable actuation, and that's why we think light could be the most important consideration for this purpose. The advantage of light over other stimuli such as electricity, magnetic field, pH, or moisture is that it can rapidly transmit energy from one source to actuators. It can generate actuation without the physical contact between from the source to the substrate, and we can also control light in terms of irradiation density, intensity, wavelength, polarization, direction. That's why we think light could be the best candidate for this one. The second ingredient is the substrate. As I mentioned, I highlighted before that polyethylene could be one of the suitable candidate for that. Polyethylene is the simplest organic material, and it's highly promising material in the domain of stimuli responsive polymer actuators. Although it was not used before, for the actuating materials, but we think that if we are aiming to create stiff polymer actuators, the chain orientation of polyethylene could give us the strongest material that we are anticipating. So the combination of low density of the polyethylene and the highest possible specific Young's modulus because of its low density and tensile strength, the negative coefficient of thermal expansion, because when we orient polyethylene, the usual positive coefficient of thermal expansion turns into negative coefficient of thermal expansion. That means that if we heat the material, it does not expand, it actually contracts because of the negative coefficient of thermal expansion. And it can accommodate any additives, and we want a photoresponsive agent to be there within the substrate. So I think polyethylene was another good candidate for this purpose. The last but not the least candidate are the ingredient for creating our actuator is a photoresponsive agents. BZT is commercially available UV stabilizer, is being used in polymers from a very long time to increase their stability towards the UV irradiation, because the polymer usually degrade with the sunlight, and they use some kind of UV stabilizers such as BZT within the polymer to increase their life. And BZT is quite promising material, and our research group recently, before our research, they showed that if we put BZT within the polyethylene, it can actually increase the transparency of the polyethylene from within the visible region. That was one of the admiring thing to be used for our research work, because we want our polymer films to be transparent so that the light can transmit through it. What happens when BZT goes into the polyethylene, it goes into the microvoids that was created because of the chain orientation, and that reduces that is because of the matching refractive index of the BZT with the polyethylene. And because of this, the light scattering is reduced and the polymer transparency is increased. BZT is not the only potential photoresponsive agent that can be used. There are others. For example, the most important are well known as azobenzenes, CNTs, graphene, pyrobenzenes, which can be used instead of BZT. However, these other materials, they either involve complex synthesis, for example, azobenzenes, because azobenzenes requires long aliphatic chains to be introduced within the polymer substrate to get it work. And or they are difficult to disperse homogeneously, for example, CNT. We want our ingredients to be low cost, commercially available, and that can be industrially viable to be created into some kind of actuators. The problem with the azobenzenes and the materials is like that they are very good in creating some sort of mechanical deformation when the polymer is soft, but when the polymer gets stiff, just like polyethylene, chain-oriented polyethylene, it's very hard to get the transformation conformation of azobenzene from trans to cis. We want, scientists have created long aliphatic chains of the azobenzenes to observe this phenomena. However, it was shown that azobenzene hardly exhibit conformational changes in ultra-dry polymers, and that observed photomechanical effects are related to thermally induced entropic effect by the embodied photothermal azobenzene agent. So again, we think that as BZT is the ideal candidate to be used because it's rather inexpensive for responsive agents. It's already being used as a UV absorber, and the absorbed energy is actually being dissipated in the form of harmless heat that can be used within the polymer, that makes it an ideal candidate for creating an actuator. In the next few slides, I'm going to showcase some of our research that has been published already. The The first attempt, we used high-density polyethylene as a substrate using BZT within it. And this is a low-cost, industrially scalable approach towards photoresponsive polymer actuation. In this work, photo actuation of melt-processed ultra-drawn films based on high-density polyethylene incorporating BZT within it was carried out. And when we illuminated the polymeric films containing BZT and then at a specific wavelength at which we can get a highest possible absorption of light in the BZT, we get a response in terms of mechanical, in terms of actuation stress. We run a simple tensile relaxation experiment. Usually what happens over here, when the BZT absorbs light energy, it converts into heat, which available to the surrounding oriented polyethylene chains, that because of the negative coefficient of thermal expansion tends to contract. But because we are running the experiment, we are holding the chain from the both ends, and because of the tensile relaxation, the strain remains at the constant level. The only thing that can change is the stress that we call actuation stress. As you can see over here, as soon as the light turns on, we keep it turned for 10 seconds and then 10 seconds off to see the reversibility and rapid effect of the polymeric of the photoresponsive agent. As you can see, we achieve a very rapid and reversible response. We actually use 3 or 4 different kinds of percentages of BZT to see if we can enhance the effect. Actuation is usually triggered by the light which was absorbed by the BZT and transformed into heat. We were able to achieve a very high actuation stress, which was around 20 megapascal. And that is because of the Young's modulus of the oriented polyethylene chains and the negative coefficient of thermal expansion. That is what we believe at that moment. At that point, we expect that the actuation performance of oriented polyethylene can be enhanced through increased draw ratio, because we believe that the effect that we are getting, the actuation stress, is actually the multiplication of the two things, which are the Young's modulus and the negative coefficient of thermal expansion. So if we increase the chain orientation, we will be able to increase the Young's modulus, and so does the actuation stress. But there is a limitation for high-density polyethylene, and also when the film thickness is higher, you can see the light cannot pass through the film completely, and thus creating a thermal gradient, which actually does not provide to exploit the full potential of the BZT within there. So we in the next phase of our research, we use ultra high molecular weight polyethylene, just aiming to get high actuation stress because of the higher Young's modulus, and the results were quite promising, and we were successfully able to get a very high actuation stress, which was around 17 megapascal, and this actually was the highest ever reported actuation stress back at that time when we did our research, as compared to other organic and inorganic materials, because of the low density, high Young's modulus of the polyethylene. And the effect was, again, rapid, responsive, and this is all because of the heat generated within the polymer substrate because of the BZT within there. Following the results shown over here, however, it was found that the actuation stress as a function of draw ratio exhibits an optimum. What we were hoping that if we keep on increasing the draw ratio or the chain orientation, the Young's modulus is increasing. Yes, the Young's modulus is increasing, but the coefficient of thermal expansion, negative coefficient, is decreasing because more and more chains are being they are being straightened, and they are showing less relaxation within their chain strength. So we got the optimum, but we need some kind of explanation what happened over there, and why this was the case over here. So in the next phase, in order to understand and quantify this behavior, the influence of solid state drying on the photoactuation stress of oriented semicrystalline polymer was explored theoretically. A semi-empirical model was created in which the impact of actuation stress and the factors that are affecting the actuation stress was explored. For example, negative coefficient of thermal expansion, Young's modulus, and the difference between the temperature before illuminating and after illuminating. The results was surprising that the negative coefficient of thermal expansion, the decrease in the negative coefficient of thermal expansion is actually counterbalancing the effect of increasing Young's modulus. And this is the only factor that comes into action is the change in the temperature. But there is a limitation between the polymeric chains. So if we are exploiting the full potential of the polymeric chain, which is somewhat over here, then we will be able to create a highest possible illumination temperature. But there is also a drawback of the polyethylene that it cannot accommodate. It cannot bear the temperature too much. There is a capacity. Otherwise, it can start to degrade. So based on these results,
Dr. Bhatti, can you please conclude that already?
Yes, the next slide will be the final one. So at this moment, after our research work, you can see that the polymers are all over the graph of the actuating family. We can see that there are polymers which are providing highest actuation stress and also highest actuation strain, soft polymers, and also the highest actuation stress, which are the stiff polymers. This is my last slide, and this is the research gaps that arises on the basis of our results that opens new horizons. For example, because of the low temperature resistance of the polyethylene, we cannot continue our work with the polyethylene, but there are other polymeric materials like polyolefin, like polyamides, polyesters that that are high temperature resistance and can be utilized for this work. We can use natural light because UV is the base to be being used to generate photoresponsive within the polymers, and that can also be explored. The application for the application point of view, I think there are some designs perspective inspired from the natures. For example, wheat-ons, self-cleaning and anti-reflection surfaces patterning of insect wings. These are the design in which these are the applications, are the examples in which design plays an important role. And we can also think about increasing the actuation strain by combining different, for example, instead of monofilament or one film, we can use multifilament or spring-like structures. And also the effect can also be generated by using heat. Thank you very much. This slide actually showing some of my research collaborations. I'm open to questions now.